So let us quickly go through what we covered last time. So we were looking at using integral methods for the thermal entry length region, and here we confine this integral method for internal flows to only Cartesian coordinate system. So since it's difficult to integrate your energy equation in cylindrical coordinate system and apply the integral technique, so most of the discussion related to integral method for internal flows is confined to plane ducts. So that is basically flow between two parallel plates. So we will take up one such example where we have a thermally developing region, that is basically region 2, where we have the fully developed velocity profile, the parabolic velocity profile, and we have applied the constant wall flux boundary condition. So when you write the velocity profile, basically you use a coordinate system which is aligned to the center of the channel. Okay, so that we have to transform to a coordinate system which is starting from the plate, because the integral method is basically integrated from the plate till the edge of the boundary layer. So that's where we transform the coordinates, and then this is the velocity profile in the transformed coordinate. Okay, and of course if you integrate the energy equation, it's a very straightforward integration, you directly get the energy integral, which is the equation number 1. So all you need to do is know the velocity profile and the guess some profile for the temperature. The velocity profile here is coming from the exact solution, because you cannot again use an integral method solution in the fully developed region. Okay, so once the boundary layers merge, then the integral method cannot be applied, because these are all boundary layer equations. So therefore we use the fully developed velocity profile from the analytical solution, but for the temperature profile in the developing region we just make a guess for a cubic polynomial as usual, and these are the boundary conditions. You specified wall flux at y equal to 0, and at y equal to delta t the gradient is 0, and the temperature at the edge of the boundary layer is equal to the inlet temperature. Okay, so from here we get, if you substitute all the boundary conditions, you can end up calculating all the coefficients, and this is the resulting cubic profile for temperature that you get. So the temperature profile is a function of your wall flux, your thermal boundary layer thickness, and of course the non-dimensional y coordinate. So we will introduce certain non-dimensional variables here. Your eta is your non-dimensional y coordinate. Same way, this is the same nomenclature I am using, similar to your external boundary layer flows. So y by delta t, and similar to your external flows where you used non-dimensional zeta for delta t by delta, here we don't have any boundary layer momentum boundary layer thickness, because we are considering already fully developed flows. Therefore instead of delta we use d here, which is the half separation distance. Okay, and we substitute this profile into your momentum integral, you integrate it out, and we neglect all the higher order terms of zeta. Since you are looking at the thermal entry length, you are supposed to be looking at region where your delta t is much smaller than delta. Okay, so therefore since your epsilon is less than your zeta is less than 1, we neglect all the higher order powers of zeta of the order of quadratic powers and higher. So if you do that, you get a direct expression for the zeta, which is nothing but your non-dimensional thermal boundary layer thickness. Okay, so from here we have to go on and get the expression for the heat transfer coefficient. So we define our heat transfer coefficient h of x, which is varying locally in the thermally developing region as qx divided by T wall minus Tm. So this is our definition in internal flows. So now we need to get the denominator, which is T wall minus Tm. Okay, so we can get T wall minus Ti from the profile that we have. This is our profile, let me call this as equation number 2. So T wall minus Ti here is at y equal to 0 okay, and we also need to know what is my T wall, what is my T mean minus Ti. So once I know T wall minus Ti, T mean minus Ti, I take the difference, I get T wall minus Tm, okay, and that will give me the final expression for heat transfer coefficient. So now we have to determine what is the mean temperature. So to do that, how do we determine mean temperature? We integrate our temperature profile. This is a mass weighted average, okay, so that is T minus Ti and weight it with the velocity, and here for the channel case we have to consider only the integration along this y. Now the velocity profile that we have, now we are looking at boundary layer growth from the top plate and bottom plate, okay, now we are focusing on only one plate at a time. So for this the velocity profile we have to consider is from 0 to d, okay, where you have your velocity profile, that is the maximum velocity there, alright. So therefore we will do this integration from 0 to d, because this is a mass weighted average we are taking, and divided by 0 to d u dy, okay. So we know that I can calculate my mean velocity based on 1 by d integral 0 to d u dy. So I can define a mean velocity from 0 till d, because the boundary layer growth at the bottom plate is affected by the velocity profile from 0 to d, and for the top profile it is exactly symmetric, okay. So I am looking at the mean velocity which is basically affecting the thermal boundary layer growth on the bottom plate, okay. So therefore I am concerned only with the region from 0 to d here, okay, not the complete 0 to 2d, okay. So if you integrate it out, so you get your relation between your 0 to d u dy as um into, so therefore you can write this as 0 to d t minus ti into u by um dy into 1 over d, okay. So now I can also express the relationship between d and the hydraulic diameter, okay. So the hydraulic diameter for the case of plain duct, we have seen that this is basically 4 times d, so therefore we can replace d by dh by 4, okay. So this will be dh by 4. So how we got this? I think all of you know, if you consider a plain duct in the 3-dimensional sense, and this is your separation between the plates which is 2d, you consider width in the third direction as w, so the equivalent hydraulic diameter here will be 4a by p, which will be 4 times 2d into w by perimeter will be twice w. So therefore dh will be 4 times d, okay. So finally this is my relationship for calculating the mean temperature. So I simply have to substitute my temperature profile into this. I know my velocity profile u by um, okay, which is, so your, in the case of channel flows, again your center line profile is 1.5 times your mean velocity, okay. So this can be substituted and you can integrate and therefore determine the expression for T mean minus Ti. So we will quickly do that. So I am substituting my velocity profile as well as the temperature profile. So this becomes 3 by 2 into 4 3k dh, and I am integrating over non-dimensional, so I am converting this into eta, which is y by delta t, okay, in place of y. So therefore I am substituting all of this, it becomes 0 to 1 essentially, and this is 2 eta zeta minus eta square zeta square into 2 minus 3 eta plus eta cube into d eta. Okay, so if you plug in for your temperature profile, which you already have it here in terms of eta, so your y by delta t here can be expressed in terms of eta, and in case of your velocity profile, your y by d can be expressed as eta into zeta, right? So you plug it in terms of eta and zeta, and you integrate over the non-dimensional y coordinate, that is basically your eta between 0 and 1. So this gives my expression for Tm minus Ti as 2q double prime delta t square by k dh, and I don't now eliminate any higher order terms of zeta. Okay, so unlike the case where I substitute into the momentum integral, and there the expression for zeta square is under the derivative d by dx. So there, if I make the approximation that the higher order terms for zeta can be eliminated, so the differential equation becomes easy to solve. Whereas here I don't have any differential, this is an algebraic equation. So I retain all the higher order terms as much as possible. Okay, so this is my expression for Tm minus Ti. Let me call this as equation number 4, and this is the expression for Twall minus Ti. This is equation number 3. So therefore Twall minus Tm can be written as Twall minus Ti minus Tm minus Ti. Okay, so you see there are common terms here. Your q 2q double prime delta t by k is common. Okay, so we will just take that out so that I can write my expression for Twall minus Tm as 2 times q double prime dh by k into zeta by 12 minus zeta cube by 40 plus zeta power 4 by 192. So in fact the Tm minus Ti can also be substituted. You can simplify this a little bit and write it in terms of zeta cube by 10 minus zeta power 4 by 48. So here I am using the relation that my delta t is nothing but zeta times d. So I am substituting for delta t in terms of zeta times t. So this becomes zeta square. So this multiplies, this becomes zeta cube here, zeta power 4, and this is my d. So this is my expression for Tm minus Ti, and this is my expression for Twall minus Ti. When I subtract both, this is what I get for Twall minus Tm. Let me call this as equation number 5. So therefore, so once you have the denominator here, so directly I can get the expression for Hx. So Hx will be nothing but Qall double prime, that is your constant heat flux applied to the plates, divided by this particular expression here for Twall minus Tm So my Qall double prime cancels here. Now I can directly get the expression for Nusselt number. You can see that this can be written as Hd by K. Okay, so my Nusselt number in the thermally developing region, which is based on the local heat transfer coefficient times the hydraulic diameter divided by K, comes out to be of this form, which is I can also take some terms common from here. I can write this as 2 by 4 and I can make it 1 by 2 here, okay, so that this becomes 3, 10 and 48, okay. So therefore this becomes 1 by 2 and goes to the numerator, this becomes 2 by zeta by 3 minus zeta cube by 10 plus zeta power 4 by 48, okay, where your zeta is nothing but we have already derived the expression for zeta by solving the energy integral, that is 80 times x by dh divided by Peclet number whole power 1/3. So this non-dimensional ratio here, Peclet number by x by d is nothing but Graetz number, okay. So you can also call this as Graetz number. This is inverse of Graetz number, so this is Peclet number by x by dh, okay. So once you basically know your non-dimensional zeta, so this gives you the variation of your local Nusselt number with respect to the non-dimensional axial location, okay. So this is the relation for the case of flat plate. Now the question is whether if you use the asymptotic value, whether the asymptotic solution leads to the case of thermally fully developed flows, that is the question. So therefore if you look at the asymptotic case where your zeta goes to very large value, okay, whether this particular solution becomes equivalent to your solution for fully developed, thermally fully developed flows, okay. So in that case, if I substitute, since my zeta is in terms of delta T by d, what happens if the flow is thermally fully developed? What should be the value of asymptotic value of zeta? 1, okay. So if for large values of zeta, so that should asymptotically go to 1. So your Nusselt number for zeta going to 1 from this expression comes out to be 7.86. Now I think in the last class I have given you a table for flow past channel, and what is the value if you apply a constant heat flux in the fully developed region? 8.23. So that is the actual analytical solution. So compare that with what you are getting from the approximate method. So it is not leading to the correct solution, you know, there is quite a bit of an error between these two values. This is because the integral method is not valid for the asymptotic limit, okay. Why? The boundary layer is merged, so therefore the boundary layer approximation is not valid anymore. And the other thing, we have in the energy integral we have neglected the higher order terms of zeta, correct? So in fact we are looking at the asymptotic case which is for the large values of zeta, and that we have neglected here. So even if the boundary layer approximations were assumed to be valid, since we have made an approximation here, so together put together, finally the asymptotic values are not that close to the exact values, okay. So therefore you should consider the integral method when applied to the internal flow case. This is a very approximate method and it is valid only in the region where your boundary layer approximation is valid. That is the initial part of the thermal entry length. If you go downstream to the place where it merges and finally becomes fully developed, then you cannot apply the approximate methods, okay. So this is to just give you an overview, one example how we can use the approximate method in internal flows, and that is also restricted to the Cartesian system, Cartesian coordinates. and again you use the exact solution for the velocity profile and you work out the case for thermal entry length. So you can do this for also a similar analysis can be done with the constant wall temperature case. So I am not going to do this. In fact, I have posted assignment number 4 on the Moodle. You can just go and check that, and I left that as an exercise in the assignment 4 where you are supposed to sit and work out for the constant wall temperature case. A very similar exercise, very straightforward, similar kind of an exercise which you did for the external flows. Okay, so I'll just give you the final solution for that before we stop the discussion on laminar internal flows. So if you consider that instead of constant wall flux, you have constant wall temperature boundary condition. Okay, so for the case again you can assume a cubic polynomial for temperature, and you should of course use the appropriate boundary conditions in this case. So rather than saying the gradient is equal to minus q wall by k, you say that at y equal to 0 your t is equal to t wall, which is a fixed boundary condition, and the other boundary conditions remain the same. You get a profile which is something like this: t minus t wall by ti minus t wall 3 by 2 y by delta t minus half of. Okay, so this is if you recollect, this is the exact cubic profile that you got for external flows. Okay, the same profile, only the non-dimensionalization is a little bit different. You have t minus t wall by ti instead of t infinity minus t wall. Here your free stream temperature is replaced by your inlet temperature at the edge of the boundary layer. Okay, so you can assume this to be a non-dimensional temperature theta for the thermal entry length problem, and your energy integral now. So this is your energy integral. This can be rewritten. So your q wall can be written as minus k dt by dy at y equal to 0. Okay, and that is equal to d by dx. You have 0 to delta t. Now I am going to use the non-dimensional coordinate for y, which I define as eta, which is equal to y by delta t. So therefore I can integrate across the non-dimensional coordinates so that limits of integration become 0 to 1. Okay, so rho Cp into u into t minus ti I can write in terms of theta. So how do I express t minus ti in terms of theta? 1 minus theta, so that becomes 1 minus theta will be t minus ti by t wall minus ti. Okay, so therefore t wall minus ti is constant because my wall temperature is constant, inlet temperature is constant. So I can introduce t wall minus ti and both sides it will get cancelled off. So this can be written as u into 1 minus theta into dy. So instead of dy I substitute in terms of eta. Okay, and if I convert y to eta I have to multiply by delta t. Okay, so there is a delta t also which is coming here. So once again this k can be written as alpha rho Cp, right? So rho Cp cancels on both the sides, and I can convert my y in terms of eta. So I have to also multiply by delta t in the denominator. So this becomes eta equal to 0. Okay, so this is my modified energy integral, slightly modified form for the case of constant wall temperature. So now I have the cubic profile, and of course the velocity profile is again known, the fully developed velocity profile. Okay, parabolic profile. So I substitute and then I proceed ahead the same way I did for the constant heat flux, calculate my mean temperature, and then finally I get an expression for the local variation of the Nusselt number. I will just give you the final expression. Okay, so the final expression comes out to be nux is equal to 2 by zeta by 3 minus zeta cube by 10 plus zeta power 4 by 48. Okay, so you can compare the expressions that you got from the constant heat flux. They are coming to be the same here. I think you have to do it and check. Probably I made a mistake here. Okay, you please check in the assignment. When you do that in the, I have given this as an assignment problem, so you please check what is the expression. So I am not going to give you this right now. Okay, so I myself have not worked it out. So you please do that and check. It has to be, of course, different. So this is to conclude our discussion on approximate methods. In the last class, I have also given you a tabulation where I have compiled all the fully developed Nusselt number values for different geometries. We start from plane duct with parabolic velocity profile, then circular duct for slug flow profile, plug flow profile, parabolic flow profile, and also for other cross sections like triangular cross section. And the order of decreasing Nusselt number starts from here. Channel flow, the highest value comes for the plug flow case with the constant wall flux, then constant wall temperature, then your parabolic flow, velocity flow. So it goes in that order, starts from 2D duct flow, and then your 3D circular ducts, and then finally your triangular cross section. So this is the hierarchy in which your decreasing Nusselt number follows that pattern. And before I conclude, I just want to talk a little bit about the project that I was thinking in mind. I also posted another document on Moodle, which you will see. It's called Project Natural Convection in a Square Cavity. I will just briefly describe the problem and also how you are going to solve it. And since you have now more than a month's time with you, I think you should probably take it up a little bit seriously and try to do the project. See, so far whatever you learnt in the class, they are all based on some theoretical discussion and deriving some analytical expressions. Okay, and that is not probably sufficient for you to gain appreciation of subject like convective heat transfer. Okay, a few of you were coming and asking me, is this subject only dealing with deriving expressions? Okay, there are so many equations and the mathematics is very rigorous, and is it limited to that? Okay, so in order to satisfy those kind of people, it's better that you also do a practical hands-on project, take up a case where you can really feel that you can apply the concept that you learnt. Of course, I'm not asking you to do analytical solutions for everything, so you can also try some numerical solutions, okay, which are nowadays gaining immense popularity and replacing the analytical solutions. So you should try that and see for yourself as a fundamental research problem how you are able to gain your better your understanding of what you learnt in the class. So for that I want to give this small problem. Of course it takes some coding. You have to write a small code based on finite difference method. It's a very straightforward technique once you know that, and the document which I posted has all the details. It has details including how to write the finite difference expression for the governing equations, how to apply the boundary conditions, and how are you going to solve iteratively, and it also gives the solution. So I want you to just simply read the document thoroughly and understand and try to implement it. It may take some time, that's why I am announcing this 1 month before your final exams. Okay, so I will just give you a brief overview. Any questions on what we have covered? I hope everything is clear. Okay, so anyway, when you do the assignment problems, I think things will get much more clearer. all right. Okay, so coming to your project, of course I am being a little bit hasty here. Before the topic of natural convection is taught to you, I am giving you the problem, but I think most of you have a basic heat transfer background and you will be able to quickly appreciate what I am explaining here. So you can consider a square cavity just for geometrical as well as computational simplicity, nothing else. It can have any aspect ratio, and you can consider that the left hand wall of this cavity is given some temperature. You can call this as the temperature which is higher than the right side temperature. Okay, so this is a heated cavity, and the top and the bottom walls are insulated. Okay, so in this case you don't have basically any flow to start with. Okay, so there is no inflow outflow here. It is just a cavity which is enclosing a space, and it's filled with fluid. And now you already know some basics of natural convection. So because of the temperature difference, there is a boundary layer growth which happens due to the density difference, and this will start a convection process. Okay, so this convection process is called the natural convection. Okay, so it's also called as a free convection. So now for small temperature differences, so in natural convection we characterize the a non-dimensional number which is called the Grashof number, also written sometimes as Rayleigh number. This is your G beta into Th minus Tc into, if you look at the dimension, if it is a square cavity, dimension is h cube by kinematic viscosity into thermal diffusivity. Okay, so this is a non-dimensional number which characterizes the ratio of buoyancy force to the viscous force, and this will give you the strength of the convection which is happening. So now you can see that is linked, the buoyancy force is linked to a temperature difference. The higher the temperature difference, the greater is the density difference, and that creates the convection patterns to be stronger and stronger. So initially for small delta t's you will find the convection pattern is very mild, and it will be mostly conduction. So if you look at the isotherms, you will find that the isotherms go like this almost, and there is a linear profile from the left to the right. That's indicating that it's conductive mode of heat transport. And as the Rayleigh number increases due to the increasing temperature difference, so the convection pattern becomes dominant, and you will see nonlinearity coming in. The temperature profiles don't look so good, and then you start seeing streamlined patterns. So initially your streamlined patterns will show a circulation like this. Later on it may become more and more convection dominated. Okay, so so you can start from Rayleigh number of say 10 power 3 and go up to 10 power 5. Okay, so from something which is close to conduction to something where you can see the dominant effects of convection, but still it's laminar. Okay, so this is what I want you to do with the project. You take a small cavity, square cavity, and you vary the Rayleigh number from 10 to the power 3 to 10 to the power 5, and you look at the modes of heat transfer. When it starts from conduction, then transition to convection, and then becomes pure natural convection. And to solve this, you don't have to solve the Navier-Stokes equations in the true sense. You don't solve the momentum equations, but you solve it in the stream function vorticity method, which I have derived in the very beginning. Okay, so we introduce a stream function and vorticity and solve the equation. So just to give you an overview how the equations look for the case of natural convection. Okay, so anyway, if you introduce your stream function, the advantage is that your continuity is automatically satisfied, so you don't have to solve for the continuity equation. And now you can eliminate the two momentum equations by taking, for example, you differentiate the x momentum with respect to y and the y momentum with respect to x, and you subtract the two, therefore you can eliminate the pressure gradients, and finally you can get a single equation devoid of pressure. Okay, so you have one variable less to solve now. okay, and therefore the number of equations also come down. So in that case your vorticity equation finally, if you do that, can be written as u d omega. So I am writing this under 2D incompressible and steady state approximation. So you don't have to look at the unsteady or transient patterns, you just directly go to the steady state and want to get the steady state solution, okay. So therefore the steady state equations will be minus g beta, it will be dt by dy, okay. So now you introduce stream function in terms of to replace the velocity in terms of stream functions. So I can say my u is equal to d psi by dy if I assume a stream function, and v is equal to minus d psi by dx. So I can write this in terms of the stream functions. So d psi by dy into d omega by dx minus d psi by dx into d omega by dy is equal to the rest of the things on the right hand side is the same. Okay, so this term is a body force term which comes in natural convection, and you take the derivative of the y momentum equation with respect to y, so therefore you have a dt by dy, and the gravity is acting downward here, right. So therefore it acts only on the y momentum equation, okay. If it was a inclined cavity, then you have gravity acting in both the momentum equations. So therefore when you take the derivative of the y momentum with respect to y and subtract it, so therefore you get this minus g beta into dt by dy, okay. So now this is your equation for vorticity. So vorticity transport equation. So this is the first equation that you have to solve, and obviously you see to solve this you also need to solve the energy equation along with it, because you need the information of temperature gradient. So therefore we solve the standard 2D incompressible energy equation. We don't use the viscous dissipation, we neglect the viscous dissipation. So and that will be u dt by dx plus v dt by dy. This is the convection term. On the right hand side you have alpha d square t by dx square plus d square t by dy square. So once again for u and v you can write in terms of the stream function. So this becomes d psi by dy minus d psi by dx. So this is the second equation. This is your energy equation. So you have your vorticity transport, you have your energy, and what else is required? Do you have enough equations to solve for all the variables? So this is the governing equation for vorticity, right? And this is the governing equation for solving temperature. But what is the equation for getting the stream function? So there we use the definition of vorticity. Okay, you define your vorticity. How do you define vorticity in 2 dimensions? So your dv by dx minus du by dy. So there we substitute in terms of stream function for u and v here, okay. So your v is minus d psi by dx, okay. So therefore this becomes d square psi by dx square plus d square, for u it will be d psi by dy. So this is equal to minus omega. So this is my third equation for stream function. So I call this as equation number 3. So therefore you have 3 equations, 3 unknowns, okay. So one for stream function, one for vorticity and one for temperature, 3 partial differential equations and 3 unknowns which you can solve by using finite difference method, and that is very clearly explained. I think all of you have some basic understanding of finite difference in the heat transfer course, in the undergraduate course already. I think some of you we have done the finite difference expressions, okay, for the 2D conduction problem, and I think all the MTech students also have taken numerical methods in thermal engineering this semester, so it should be fairly straightforward to express all the derivatives in terms of the finite difference expressions. So you can have a look at the document I have posted, and that clearly gives you how to write the finite difference expression for each of the derivatives, the first order derivative, the second order derivative, and so on, and you solve these equations together iteratively, okay. So solution for omega requires of course the knowledge of stream function as well as the temperature. Solution for temperature requires the knowledge of stream function. Solution for stream function requires the knowledge of vorticity. So all these 3 equations have to be solved simultaneously, but it can be solved iteratively, okay. That means you don't have to invert a matrix together. So first you start with the solution to stream function equation, where you guess a value for vorticity field to begin with, that is the initial guess value. You solve this and get the field for the stream function. Once you have the stream function field, you come to your vorticity equation, make use of the guessed value for, so that is your iterated value for the stream function, the field that comes out. So that field you make use of, you also guess the field for temperature and use this equation to solve for the vorticity, okay. Once you have the vorticity field and your stream function field, then directly your temperature field also can be solved. So like this you keep solving, take the newer values, the latest values, use that in the next iteration and so on till the difference between 2 consecutive iterations is very small. You can use that as some 1 e power minus 5 or 1 e power minus, the same way that you are using shooting methods, okay. You have a convergence criteria and then finally stop, and then when you plot these contours in MATLAB or wherever, TechPlot or MATLAB, and you will find these nice convective patterns in terms of stream function. If you plot, you can directly find out the convective patterns, and isotherms also can be plotted. So and coming to the boundary conditions, to solve this you need boundary conditions, okay. So the boundary conditions here, as far as the temperature is concerned, these 2 left and the right walls have fixed temperature, so you know the temperature at those points, you don't have to solve them. The top and bottom have adiabatic conditions, so in the simplest case will be extrapolation from the inner point. So you divide the domain into, of course, your grid, which you all know, and you have your locations where you are solving for the governing equations, and then at the boundary at the top and bottom you simply extrapolate from the interior point, okay. And for as far as the boundary condition for stream function is concerned, you have to apply the no slip condition at the walls, u equal to 0 and v equal to 0. What does it mean in terms of stream function? It means my d psi by dy equal to 0 and d psi by dx is equal to 0. So if I take the value of stream function, say at this bottom left corner as some 0, I can take any value. So the thing is, the boundary condition for stream function is in terms of gradient, so it does not depend on the value as long as the gradient condition is satisfied. So if you take for example the value here as 0, then you can look at this isothermal wall, you can apply d psi by dy 0, so therefore the stream function has to be 0 everywhere, okay. So if it is 0 here, again for this wall you can apply d psi by dx 0, right. So therefore it has to be 0 here, even here. So therefore in all the walls you can directly put stream function as 0, okay. And for vorticity you can use the remaining condition. For example, for the left wall you have used d psi by dy as 0, but you have not used d psi by dx is equal to 0. So this can be used in the vorticity condition. So you have the expression for vorticity here. So for the left boundary, your d psi by dy is equal to 0, therefore your d square psi by dy square is 0. So this will be 0 for the left boundary. Okay. So therefore your vorticity is d square psi by dx square. You can write as simple Taylor series expression for the boundary in terms of the interior point, and you can express this in terms of the vorticity at the stream function at the boundary. So therefore you can directly calculate your vorticity at the boundaries. So all this is very clearly explained in the document. Okay. So please read through the document. If you have any questions, you can ask me. Okay, but it's very straightforward, and just you have to construct the finite difference expressions, and you will be therefore converting the partial differential equation into a set of algebraic equations. So that is the method how you have to numerically solve differential equations. Finally you get a resulting set of algebraic equations which you solve by any method, whether you have to consider this as a matrix and use inversion methods or do iteratively. Okay. So here you can do a very iterative solution which is going to take only a few lines of code, do loops where you just iteratively keep doing it till the convergence criteria is satisfied, and then you can plot plot the results for streamlines. Already in the document for 10 power 3 I think he has given the streamlines, and also for 10 power 4, and you should also plot the Nusselt number that you get, okay, as a function of the Rayleigh number. I think in the document he has also given that you have, for you start with say 10 power 3 and then say 10 power 4, 10 power 5, and then so you can stop with 10 power 5, just a representative, and you can see the computed values which he has given there and your computations. You compare both of them on the same plot for Nusselt number. Apart from the Nusselt number, you also have your stream function which you have to plot and compare with his stream function, and you also have your isotherms which you can plot. Okay, so this gives you a very good idea practically how you solve the Navier-Stokes equation in two-dimensional case. So there you have the gift of basically reducing that in terms of stream function vorticity, and you can get a direct solution through differences, and I think that will hopefully give you a better appreciation of subject when you go to the research level. Okay, in research level we need not do everything by similarity solution, so that gives you also an exposure to using some numerical methods. Okay, so the deadline for the submission of the project will be on the last day of the class, or maybe if required you feel some difficulty, then we will have it on the day of the final exam. Okay, and my suggestion is that if you feel that individually you have problem working with it, you can also discuss with your colleagues. There is no harm in discussion, but whatever code that you write should be individual, it should not be copied, and you have to submit your code along with your report.